Alaska Tech Talk, Alaska Tech Talk number 26 already. My name is Ariane. I think most of you know me. I am Alaska's community manager, and I am happy to moderate the session today, which is being recorded, by the way, so please be aware of this. We will upload this later to YouTube. And yeah, the Alaska Tech Talks is a format hosted by the Alaska Association, which is focused on developing open source technologies in the context of cloud infrastructures. And we also really like talking about tech on different, levels. And the Tech Talks is something where we are going very deeply into the technical aspect of things. And yeah, this is why we are here, and I'm happy to see all of you. For the agenda today, it's the same as always. We will hop right into today's Tech Talk and have time for discussion afterwards. Then we have some news and events to share. And then I have the date for the next Tech Talk that you can save and then hopefully join again. All right, let's look at today's Tech Talk. I am welcoming Tobias Nöthlich. It's nice to have you here, Tobias. Tobias is a research and development engineer at D3TN. D3TN is actually a founding member of Alaska, so this is very lovely. And Tobias will be talking about operating applications via Kubernetes in delay and disruption-tolerant networks. And I think this is all that I have to say, and I would hand the stage right over to you now, Tobias, and stop my screen sharing.
Right, thank you. So let me share my screen really quick. So let's see, I hope it's visible for everyone. Yeah. All right. Right, then thank you very much for this very nice introduction. So as Ariane already mentioned, today I'm going to be talking about operating applications via Kubernetes in delay and disruption-tolerant networks. For this, I'm going to briefly introduce who we are, what we're doing, why we want to build a space cloud, and then go a bit more into technical detail of how we're doing this. And yeah, let's go right into it. So D3TN is a small team here in Dresden, founded in 2015. We have offices in Dresden and Miami. Our core competencies lie in delay and disruption-tolerant networking, which is also very important for the talk I'm giving today. So we're focusing on space and underwater communications. We have our own implementation of the bundle protocol, which is used in delay and disruption-tolerant networks called micro-DTN. But we're also doing simulation and development of network protocols and architectures, as well as SDN, and working with cloud platforms such as OpenStack and Kubernetes, including the operations of these cloud platforms. Business model combines contract engineering with trainings, courses, and R&D activities. And these R&D activities are exactly why I'm here today, because we're trying to build a space cloud at the moment. You may ask yourself why a space cloud isn't a cloud on Earth enough. Well, traditional space missions rely heavily on dedicated hardware and single-use applications, which means that, bit over the top, if you want to take a photo of the moon, you build a satellite for it, send it up, and once the photo has been transmitted back to Earth, you just discard it. It's not that bad, but that's the general idea, right? So this results in high development costs, limited reusability, and unnecessary environmental impacts, because you always have to launch rockets, which is obviously not quite good for our environment. So we thought that maybe it may make sense to transfer things that work well in current cloud technology to the space domain, such as ubiquitous access for services and data, scalable and flexible computing resources, high availability and fault tolerance, which is actually quite an important point. You can't just send an engineer to space to fix your satellite. And it is also going to be quite a bit more cost effective to just rent space on a satellite instead of launching your own. However, this is not quite as easy as it sounds, so we can't just throw a Kubernetes on the satellite and call it a day, because there are some limitations. Cloud technology obviously has been built for use on Earth. This means it assumes continuous low latency connectivity and is not designed for extreme latencies and disruptions, which is something we face in space. There's also no standardized execution environments for space agencies, which limits adoption, and the tenant separation for space hardware software platforms is lacking, to say the least. So if you have your highly classified research project and you have another tenant on the satellite, there well, is grounds to assume that there may be access to your data, and this is something we obviously do not want. Now, The biggest problem on the networking side is that we're networking in space, right? There's two main challenges. First of all, disruptions, and second, delays. Now, disruptions occur quite frequently. For example, if you're looking at a low Earth orbit satellite which orbits around the Earth, right? So you have the Earth, you have your satellite, and your ground station is in Germany, for example, and then the satellite is obviously not going to stop over your ground station and wait for your data transfer to complete. So it will move further around the Earth. And once it's on the backside, there's no connectivity. So this does not play nicely with the traditional networking, such as TCP/IP. It does not play nicely with Kubernetes and other cloud software that is used on Earth. And this is something that needs to be addressed. The second point, delays, is especially prevalent if we're looking into deep space missions. So, for example, if we want to send a command to a node on Mars, in the worst case, this is going to take 22 minutes for a single trip. So if you, I don't know, want to fetch some data, you send the command up, this takes 22 minutes. Your rover or your satellite around Mars will process this request, send it back. This takes another 22 minutes. So we're looking at a 44-minute round trip time, which is also not quite nice for TCP/IP and also not quite nice for Kubernetes. Luckily for the networking part, at least, there is a solution, which is delay and disruption-tolerant networking, which I'm going to introduce in the following slide. So basically, this is a network architecture which is designed for especially environments where we cannot guarantee continuous end-to-end connectivity. As mentioned, this includes space missions, but there are also terrestrial use cases where this is needed. For example, in disaster zones where the infrastructure collapsed, or underwater networks where we cannot assume that nodes will always find an end-to-end path to another destination. So DTN works on the principle of store, carry, and forward. And this means that instead of requiring a complete end-to-end path, data is sent hop by hop instead. And each node can temporarily store the data in a persistent storage until it has a contact or a window of communication opportunity to another node in range. These contacts can be scheduled. For example, in satellite networks, we can, very accurately calculate when the satellites will be in range. They may also be predicted, or they can be purely opportunistic. For example, in mobile ad hoc networks where we cannot predict where the nodes are going next. Now, let's have a look at the figure on the left. We can see a sort of overview of the DTN architecture stack across 3 example nodes, right? And the one thing that distinguishes DTN from traditional networking is the bundle layer, which is marked in green here. It sits above the transport layer, is connected to the transport layer using a shim layer called the convergence layer, which basically offers interfaces to the lower layer protocols. And what this bundle layer does is basically it establishes an overlay network which abstracts away the underlying network heterogeneity. So this means that DTN can bridge across different protocol stacks and disconnected subnetworks. For example, here we could say DTN node 1 is a node on Earth, which is in a TCP network, and DTN node 3 is a node in space, which is connected using a space protocol such as the LIC-LiDAR transmission protocol. And then we would have node 2, which could bridge these two, right? So the flow would be that DTN application generates some application data. This is sent to the bundle layer. The bundle layer would encapsulate this in a protocol data unit called a bundle, which besides the application data would also contain metadata required for forwarding, for example, or custody transfer, or also expiration. And this bundle would be sent out using a convergence layer. This convergence layer would have an adapter, for example, for TCP, so a TCP convergence layer adapter, which would then just send the packet out using TCP. It would be transmitted normally using TCP, would arrive at DTN node 2, be received by a TCP convergence layer adapter, sent up to the bundle layer. Bundle layer would inspect it, route it, see, okay, we need to send it to node 3. Node 3 is reachable via LTP, so it would be sent out using the LTP convergence layer adapter, and ultimately arrive at node 3, where another application is waiting for the application data. Now, if we look at the figure on the right, this is basically this example, just in another way, or illustrated in another way. We have the passage of time on the x-axis and spatial location on the y-axis. And we can see that we have 3 nodes, node A, B, and C. And in this example, node A may want to transfer a bundle to node C, and does so by transferring the bundle to node B when they are in contact with each other. Now, B does not necessarily have immediate access to node C, so it would first store the data until it later in the third time interval would come into contact with C. This would complete the relay, so it would send the data to C, and we would have successfully transferred data from A to C without A and C ever being connected simultaneously. And this is basically how DTN bridges delays and disruptions. And with this, the question of how to communicate in these networks is fundamentally solved. Now, what remains is the question of if it is possible to deploy cloud-native applications into such an environment. And this is what we are tackling with the DARKSOL project. Now, DARKSOL is an abbreviation, stands for DTN-Architekturen für Space Cloud Operations und Space Cloud Lifecycle Management. And this is a project we are doing with two partners. So we have the University of Dresden and Cyrus Technology, also from Dresden, on board. Project is co-funded by the European Union and the state of Saxony and the project partners. And because the topic is quite large, we split it into three main research areas. So TU Dresden will tackle delay and disruption-tolerant cloud infrastructure, basically providing the platform for deploying applications. Now, Cyrus Technology will look into building a secure separation layer for multi-tenant operation, because as mentioned, we want to have a very secure, a very strong tenant separation. So we make sure that everybody has, well, their own data and nothing else. And lastly, we as D3TN are going to be looking into delay and disruption-tolerant application operation, which is also what this talk is going to be about. Now, what we have so far is an overview of the architecture. As you can see, the Space Cloud consists of individual clusters that can exchange information via non-persistent, potentially episodic, and potentially high-latency links. Each cluster contains at least one, usually multiple nodes, and a node may be a satellite, it may be a space probe, it may be a satellite phone, maybe a computer, or anything else that can run the DARKSOL execution environment. Now, each cluster must have at least one node responsible for managing the cluster. This is a standard, it's also done on Earth. And these nodes may also simultaneously execute workloads. Now, a cluster may include nodes both on Earth and in space. This is illustrated here in cluster 5. However, there must be a persistent low latency connection between them. In the example here, these are geostationary satellites, which means they are not going to move. They will have a stable connection to the satellite phone on Earth. This can be applied to other celestial bodies as well. So we could have also a node on the moon, which communicates with nodes, satellites that are well, lunar stationary in this case. Now, a cluster which is located in Earth's orbit but does not have a persistent connection to Earth may also exist. These are LEO satellites, so low Earth orbit satellites. As mentioned, they are going to orbit around the Earth. They're going to lose connection to the ground station, which makes this an episodic link. But they are still expected to fly in a constellation or other formations so that the links between the satellites are low latency. What's more, so we can have isolated clusters. Isolated clusters are clusters which were initially set up as part of the space cluster, but then lost connection for whatever reason. So it could be because they moved away, could be because of a malfunction. Point is, they will still execute their workloads, and as soon as they get connectivity back to the space cloud, they can upload their data. We can also have deep space assets, so for example, around Mars. These will be connected using high latency links, and they may also require using relays. And these relays do not necessarily need to be part of the space cloud. So we can have data relays which just act as relays. They do not have the space cloud execution environment. They're just forwarding data. Now, the question is, we're talking about clusters. How do we do these clusters? Well, we thought that Kubernetes might be a good way. Because Kubernetes obviously has a very nice ecosystem, a thriving ecosystem, is widely used, offers a few benefits which are quite nice. So for example, self-healing is something we want in space because, as mentioned, we can't send somebody up to fix something. Now, what could this look like? So in the example of cluster 2, we could have a cluster that looks like this, right? We have a satellite which acts as the control plane. This runs on a single satellite in the cluster or maybe multiple satellites. And this control plane hosts everything that's needed for managing the cluster. So the scheduler, for example, the controller manager, the etcd database, and the Kube API server. Now this cluster manager, the control plane, is connected to the other nodes in the cluster using intra-cluster inter-satellite links. As mentioned, these are expected to be stable at low latency, and then they can schedule workloads on the worker nodes. So far, so good. Now there is a problem because we are missing a component. We talked about communicating inside of the cluster, but we still need to communicate to other clusters and especially the applications in these clusters. And this mode of communication needs to be delay tolerant. So what's the plan on addressing this? Well, we need to do 4 things. First of all, we need to build an application which can be deployed to the cluster, or at least a use case. Then this needs to be deployed to the cluster, which means this obviously needs to be delay tolerant because we're deploying from Earth to space. We need to send application data to other clusters, and we need also to be able to receive data from other clusters. So let's dive right in. So what have we thought of? Well, we want to build a distributed machine learning pipeline for image pre-analysis in space between a Kubernetes cluster in the ground cloud and a Kubernetes cluster or multiple Kubernetes clusters in the space segment. The space clusters are going to be inference or doing inference and data collection. And this demonstrates very nicely the deployment, sending and receiving data aspects. Now, how would this look like? Well, first of all, we would have a model training phase on Earth, right? So training is done on very capable hardware. This would not be possible on satellites. We would distribute this model from the ground cluster to the space cluster, do inference, run inference on the space clusters, and send the data back to the ground cluster, where it could then be used basically to, sorry, 1 second, to improve the model again, forming a cyclical progress here. Now we know what we need to deploy. The question is, how do we deploy it? Well, we thought about using Helm for this. Helm is a Kubernetes package manager, which uses charts. It's reusable, or charts are reusable version templates for deployment. This allows for easy upgrades, rollbacks, and release tracking. And what's very nice for our use case is that it is easily extendable through so-called plugins. Now, building an extension is actually quite simple. It's just 5 steps. You need to install Helm and the plugin SDK. You need to create a plugin directory, add a YAML file which describes your plugin. This contains metadata such as the name, the version, usage, and the command. And then you basically just need to build an executable script or binary which performs whatever action you want your plugin to perform. Make it executable, place it in the plugin directory, and it's ready to go. So what have we built? Well, we have built a Helm extension for DTN installation, or installing over DTN. And the idea here is that you invoke Helm DTN install on your command line, and then Helm will package everything it needs to install a certain chart into a tar file, send it to micro-DTN, which, remember, is our own DTN implementation, which will then send this tar file over a delayed or disrupted link. So this micro-DTN instance is then basically in the space cluster, will receive this file, this archive, and send it to the application lifecycle management controller. So this is something that micro-DTN can do. We have a so-called application agent protocol, which allows applications to connect to a micro-DTN instance and register an endpoint for either sending or receiving data. So in this case, the application lifecycle management controller would register an endpoint at micro-DTN, receive this tar file, extract it, fetch the images from the registry, and instruct Helm to deploy the application. So this is a first version with one major drawback. We are still expecting every image to be preloaded in the registry. In the future, we want to develop a sort of mechanism for transitive dependency resolution, so that basically on Earth, we are already packing everything, including transitive dependencies, into this tar file, so we can send it and deploy it on the space cluster without having to, look for missing dependencies. So now we know that we can deploy application. We know what application we want to deploy. We know how to deploy it. What's next? Well, the application, needs to be able to actually communicate, either with the ground cluster or with other space clusters. And for this, we are building a delay-tolerant ingress and egress. The idea here, this is a first draft we had, was to have a bundled processing agent, which would do the delay-tolerant communications between the clusters. So in our case, micro-DTN. Then we will also need a DTN ingress for forwarding data to the application, a DTN egress for forwarding data from the application. And these, connections should ideally use an existing protocol, the application agent protocol I mentioned earlier, which registers endpoint at the BPA resource and can then receive or send data. So we also have built a small demo application because the application for machine learning is not quite finished yet, which basically uses ingress and egress to test if everything works. So let's go a bit more into detail, starting with the egress because it's a bit simpler. The egress is basically just a Python script which acts as a mapping component. It registers a endpoint at micro-DTN and basically abstracts this whole endpoint registration thing away from the application. The application will just need to connect to the egress gateway, which would then tunnel all the traffic to micro-DTN, which then sends it out over the network. So how is this done? Well, this is an implementation of a Kubernetes custom resource definition managed by a designated controller written in Go using KubeBuilder. And it has 4 operational phases. So first, we are deploying it to the cluster. This causes the controller to spawn a deployment, which contains a set number of pods for the egress proxy, which then connects to micro-DTN and registers an agent ID for sending. This is basically all the proxy needs to do. It will then wait for a connection from an application which wants to send data over the DTN, and then, well, basically we'll just tunnel this traffic to micro-DTN. Once the connection is done, it's closed, and it goes back to waiting for a new connection. So pretty simple. The spec is also pretty simple. We basically have 2 fields, a DTN backend field for defining the target DTN software stack service, and the egress proxy field for defining the configuration for the intermediate egress proxy deployment and service. For the DTN backend, we need a name, namespace, and port to basically connect to the service, and we need the agent ID that the egress proxy should register with the DTN software stack. Now, for the egress proxy itself, we need a port, basically just a port. It will listen on for incoming traffic from clients. We need an image, a destination EID, which is the endpoint where the proxy should send the data, and a secret for authenticating against micro-DTN. And then we can also specify how many replicas we want and which logging verbosity the proxy should have. So here's an example configuration. This configures a DTN egress which connects to micro-DTN via AAP on port 4242, registers the test agent, and listens for incoming connections on port 8080. Here are 3 things which I highlighted. The agent ID and the destination EID are statically configured, which works very well for our test setup, but obviously when you're deploying it productively, you may want to change the agent ID it uses to register in case, for example, an application expects a response. And you also want to change the destination EID because not every application will want to send data to the same endpoint, obviously. Third arrow points to AP2 secret. This obviously needs some kind of secret handling, but for the development purposes, it works. Now, the ingress is the second component, which is also a Python script, which also registers agent with micro-DTN and forwards data addressed to these agents to the right application. Also implements an AAP2 client for connecting to micro-DTN and sending the data to the applications, and is also implemented as a Kubernetes custom resource, part of the same API group as the DTN egress. Operational phases look very similar. We are deploying it to the cluster. The controller will create a deployment, spawn the pod. Pod will connect to micro-DTN and register the configured agent IDs. In this case, it could be multiple agent IDs because, well, maybe an application wants to have multiple routes or we have multiple applications. It will then connect to the applications and tunnel traffic from micro-DTN to the applications. So I mentioned it's implemented as a Kubernetes custom resource definition, maybe a bit of our process of getting there. First of all, we wanted to implement it using the Kubernetes Gateway API. So the very, very first idea before really diving deep into how the Gateway API works was to have the ingress proxy be the gateway. So this would correspond to the original sketch I just showed earlier. So we would have a gateway class DTN ingress, and the gateway spawns the DTN ingress proxy, which would then connect to the applications in some manner, which could be a TCP route or a plain TCP connection. However, everybody who works with Kubernetes probably already thought, why would you do it that way? We found out later that this is not the best way to do it because it will violate the Gateway API standard. The Gateway API wants to register listeners and expects to be the first point in the cluster where the traffic is basically received. And if we do it like this, this would not be the case because we would still have micro-DTN on the edge, which would receive the data and forward it to the DTN ingress proxy, where we would then need to map it to the listeners and somehow forward it to the application. And this is obviously going to be very confusing for people who are used to the way the Gateway API is used normally. So we threw this idea out and evaluated spawning micro-DTN as the gateway. So gateway class still DTN ingress. Gateway would now spawn directly micro-DTN, which would fix the issue of that we're using the listeners in a non-standard way. However, there's still some problems. So first of all, no support for DTN protocols, obviously, would require a custom route type to actually connect to the backend because micro-DTN uses the application agent protocol, which I mentioned before. And the gateway API by its very design is more or less built around the paradigm of real-time connection-oriented network ingress and routing, right? So its core concepts like the listeners or the protocol forwarding, the immediate routing to the backends are more optimized for low latency, always connected environments, how we find them in TCP or HTTP environments. And therefore, the gateway resource is more or less fundamentally about managing an ingress point for live traffic. And while we more or less do this here by spawning micro-DTN, micro-DTN is doing far more than just forwarding bytes, right? It is doing the bundle processing, the persistence, the custody transfer, the routing. And these DTN-specific operations have no direct equivalent or abstractions within the gateway API's listener or routing models, which means it would still be confusing for somebody who hasn't used DTN before to use it to spawn a DTN gateway. So we discarded this idea and focused on building a custom resource instead, which looks like the following. So this is the spec for our custom resource. We have a gateway field, which defines the DTN software stack where the agents should be registered. We have an image, which defines the configuration, obviously. We can still say which logging verbosity, which we want, how many replicas should be created. And we can define applications. And this is an interesting field because this is a list of backend application connection details, which also tells us which routes we want. So what does this look like? Basically, the applications field consists of a service name and namespace for an application. So we can connect to this application. And then we have a routes object, which consists of an agent ID, which is a string, which is the agent ID that is registered with micro-DTN for this specific route, and a port, which is the port on which the route connects to the application. If we look at this in the example configuration, what we are doing here is basically spawning a DTN ingress, which connects to micro-DTN via IIP on AIP2 on port 4242. And in this case, under the applications, we have one application. We have the Time Echo application, which is our demo application, which is reachable via Time Echo service in the default namespace. And we only have one route. The route has the agent ID Time Echo, so this is what would be registered at micro-DTN, and it has the port AE81, which would be appended to this URL that is used by Kubernetes for connecting to the application. So we would forward data addressed to Time Echo to port 8081 of the Time Echo service local Time Echo service default SVC cluster local URL. Same as with the egress, we still have the AAP secret in plain text. As mentioned, we're going to address this down the line. Right, so this was a lot of input. So let's quickly recap what I've talked about. We want to bring cloud-native applications to space. And for this, communications need to be delay tolerant because we cannot assume consistent end-to-end connectivity. We try to get there by implementing delay tolerant ingress and egress in Kubernetes and building a delay tolerant deployment mechanism using Helm. This is a first step to achieving this goal. And for now, we have a DTN egress class, which allows for delay tolerant communications from the application. And we have a DTN ingress resource for delay tolerant communications to the applications. Now, what are the next steps? Well, we thought about consolidating the ingress and egress into one resource. That would make it more clear and a bit easier to deploy and configure. We want to address the open issues I mentioned throughout my presentation. So, for example, the secrets handling and the configurability issues. And we also, this is the next big point, want to research ways to share connectivity information with other nodes. So for example, if you have two clusters, cluster 1 and cluster 2, then we want cluster 2 to be able to somehow discover that there is a specific application deployed in cluster 1. Right, so this concludes my tech talk. I hope you found it interesting. I hope it's a new topic for some of you, which you have not heard about before. If you have any questions, I'm sure there's going to be a Q&A after this, but you can also write a mail to one of the addresses on this slide. Yeah, once again, I hope you enjoyed it. Thank you very much for your attention.
Yes, thank you so much, Tobias. This was super interesting and definitely like something else that we haven't discussed here before. Yeah, I would give it over to the audience. Are there any questions or comments? I see a question in the chat. I can read this out. What are usual performance specs of a modern satellite, CPU, RAM, etc., and how much overhead would the Kubernetes control plane impose on them in relation?
So we are actually building a realistic testbed using some boards, which could also be used on satellites at the same time. And we think that the overhead imposed by the Kubernetes runtime is negligible. So it should not be enough to really make a difference for the satellite.
Great, thank you. Any other questions or comments? There's one more coming in the chat. Do you use a special Kubernetes distribution?
Depends on testing. So for the local environment where we just spin up a cluster in an LXD container, we are using K8s. But for the actual testbed, we are evaluating using Talos, the Talos Kubernetes distribution. We also thought about evaluating ones with the ALASCA Kubernetes distribution, right? But this has not happened so far.
Thank you. Anything else? There's another question in the chat. Oh, give me a second. Is potential data loss and necessary retransmission a big problem to address in this context?
Possibly, yes, but this is indirectly addressed through the DTN or through the latent disruption-tolerant networking because the bundle protocol basically offers some mechanisms for retransmitting bundles if they are lost and accounting for whether bundles have been received. And so we do not necessarily need to tackle this specifically. But yes, obviously, if you're in space, then there is going to be data loss, maybe connections abruptly ending or bit flips or whatever. That data is unusable. So yes, it is a big problem.
Okay, I will wait a moment if there are any other questions coming in. I think that doesn't seem to be the case. But yeah, as you mentioned, if there are any questions afterwards, people can reach out to you. And so yes, thank you so much again for giving this talk. And then I think we can move over to some infos from the community. Let me briefly share my screen. Yeah, let's look at things that have been going on in the past month of June. We've had the Alaska Hackathon, and I think Helena is here to give a little report because she was there and has been organizing this.
She's here. I'm sorry, I can't really turn on my camera right now. I can't seem to find a way to do that. Yes, I would like to thank everybody again for joining the hackathon in June in Stuttgart. It was really great. We got a lot done. We had a list of a couple topics that we were able to work on, and we got some real results, which we're always very happy about. And I hope everybody had a great time. I'd like to thank Uhuru Tech again, which I think no one's here from Uhuru Tech today, but everybody else hears it. Thank you so much again for your help and for all coming together and doing the hackathon with us. We are very appreciative and we can't wait to do another one with you guys.
Yes, thank you. I don't know if someone has to add something who was maybe there. If not, we can move over to the next topic, and you can keep the microphone, Helena, and continue sharing.
Oh, okay. These are all my topics. Okay, I see. Well, in addition to the hackathon, I'd love to talk about the white paper again. We talked about it yesterday in our marketing meetup, but this is a new group of people. So we just recently published this white paper on the topic continuity on the path to digital sovereignty, European initiatives in focus. This is it's kind of a report, or as it says, like a position paper on the Alaska Roundtable that we had in Berlin in March. And we would love it if this white paper could be shared by you. You can find it on our website, you can find it on our LinkedIn, and we'd love it if that could be published by some of you guys, so we can broaden the communication on this topic a little bit. I can see a comment in the chat. Okay, just sponsoring. Yes, Matthias, you're right. I forgot about that. Thank you so much, B1 Systems, for sponsoring.
Mm-hmm. All right, and then I think we have another topic about the Alaska Summit. So maybe you can continue.
Yes, I can. Alaska Summit, the big event of the year. It's coming closer, very fast, kind of. It's happening on November 3rd and 4th at the Deutsche Hygiene-Museum in Dresden, which is the same location that it was last year. Under the motto, not from Alaska, from Europe, built for Europe's cloud future. And we currently have a call for contributions open, and we would love it for everyone who hasn't, maybe, to use this chance and turn in your contributions if you have any. It's open until June 30th, so that would be very great. We can't wait to see all your contributions and then kind of puzzle and make a great program out of it. Also, there is always sponsoring. There's a couple of sponsoring options that we still have open. So if you have considered sponsoring the event, we would be very, very grateful if you could just reach out, and then we can talk about the options that are still currently open. And that would be very, very great. Thanks.
Thank you, Helena, for the update. And yes, again, thank you, Matthias, for bringing up the sponsoring for the hackathon of B1 Systems, which has been very, very helpful. And it's really nice to see the community coming together to make this all possible. We do have, I think, a little bit left that we can talk about. First of all, other events from the community. I know we have the save the date for the SCS Summit in September and the OSBA Connect in November. I don't think anyone from that community is here. But yeah, just so that you know, are there any other interesting news or events that you would like to share? If not, then we have to make another announcement, a very lovely one. We have a new Alaska member. The community is growing. So welcome Pacifico Digital Explorations. I think a lot of you are already familiar with the team. They were at the hackathon. They also gave a tech talk. And I think we also have someone from the team here. Maybe you want to say something?
Yes, thank you, Ariane. Yeah, we are really happy to be member of Alaska now. So we've been to the Alaska Summit last year, and it was really inspiring for us. Also, like shaped our open source journey, like a lot. So nothing we had guessed like before joining the event, but now we are here. This is cool, and yeah, as Ariane said, we've already been to the hackathon, and we're going to have a talk at the Alaska Summit as well. I mean, unless you won't want to choose it, but I don't think so. And we are web developers, and we are developing an open source framework for platform and portal development called Raclet. And we're hopefully also think of finding a nice use case for Raclet within the Alaska community. Also, if you have any need for cool front-end designing, like it's very easy with a framework. But we really love digital sovereignty and open source, and we love how the community has the same values as we do. So yeah, it will be great.
Thank you so much. Yes, welcome again. I hope you will have a fantastic time in our community. Before we finish this, a brief look or call to action for this format for the Alaska Tech Talks. We are currently figuring out the pipeline for the next months, but I know that we have at least one free slot, which is September or October. No, maybe November too, sorry, but somewhere around that. If you have an interesting topic that you would like to present, or you have heard of something that we maybe could reach out to, we are always happy to receive your input and continue this format. So with that, I think we are finished for today. The next Tech Talk will be July 25th. We are currently confirming what it will be, but we do have something in the pipeline, so we will share this soon. So yeah, I wish everyone a beautiful weekend. If you're going on vacation, maybe in the next few weeks, have a great time. And yeah, otherwise, we will see you next time. And it was nice having you here. Bye, everyone. And also, sorry, and again, Tobias, thank you so much for being here. I forgot that. So thank you again for giving this talk today. But yeah, with that, have a nice day.